Let's look at the work, energy and power problems involving the principles of momentum and impulse. The first example says, a demolition ball is used by a demolition truck with a crane system to break the wall of a building. The demolition ball of mass 1250 kg is lifted by a crane system to a point A at a height 5.8 meters above its lowest swinging position. The demolition ball is then released from point A and strikes the hole at the lowest point of its swing, B. The ball continues to move horizontally inside the hole until it comes to a stop after 0.5 seconds. Calculate the magnitude of the average force exerted on the ball by the hole while it moves into the hole. For 8 marks. Make sure you pause the video and try this yourself. We are given a height from the bottom of the swing position to the ball, which is 5.8 meters, and the ball will swing from position A to position B just before it hits the hole. Let's define the direction of motion as to the right as positive. So all the terms that are going to the right, if they are vectors, we have them as positive values. All the vectors that are going to the left, we have them as negative values. Let's look at the swinging motion from position A to position B. So this is just before it strikes the hole. Remember, the ball doesn't stop swinging here. I just paused it so that we can calculate the velocity just before it strikes the hole. This video is part 2 on the video that I made on energy principles. So make sure you watch that one first before you go to this one. On the swing motion from position A to position B, we know the total mechanical energy of the ball is conserved. So we can go and write the equation for energy conservation, which says the initial mechanical energy is equal to the final mechanical energy. Now we can go ahead and cancel terms that we know are 0. Let's go term by term and look at terms that are 0. The initial kinetic energy, is it 0 or is it not 0? So does the ball have initial velocity before it is released? No. So at point A, the ball is still or at rest. Let's go to the second term. Does the ball have potential energy at point A? Yes. Reference to point B, the ball has a height of 5.8 meters. So that term is not 0. So on the other side of the equal sign, does the ball have kinetic energy at point B? Yes. So the ball will have a final velocity at point B. That term is not 0 as well. The last term, does the ball have potential energy at point B? No, because point B is actually our reference position. We can take that B as the ground position. So there's no height there, which means this term falls away. We can then substitute all the terms that are remaining. We know the mass of the ball is 1250. The gravitational acceleration is 9.8. The height initial is 5.8. And half the mass multiplied by the velocity at position B final. Now we know that the only unknown that we have there is velocity final squared. So we can find the value of that, which becomes 10.66 meters per second. Now let's go to the diagram and look at what happens when the ball strikes the wall. So now on the motion of the ball into the hole, remember we say the ball is moving horizontally into the hole. So for a small distance, the ball will actually move horizontally. We can write the equation for the impulse momentum theorem, which says F net change in t is equal to change in momentum. This is because we have the final velocity and the initial velocity of the ball, and we have the duration the ball takes traveling inside the hole. So then we can find our average force. Remember, we chose to the right as positive. So we can draw a free body diagram on the ball as it strikes the hole. We know that there is a force that the hole pushes on the ball as the ball now penetrates the hole. Since we only consider only a small distance when the ball penetrates the hole, we do not take into account the tension in the rope and the FG that is going straight down, because those two forces are now perpendicular to the direction of motion of the ball. So if we expand our equation, F net is just the negative F wall, because it's going in the negative direction, multiplied by change in T. This is equal to the momentum final minus the momentum initial. Then we can cancel terms that we know are zero. So the negative F wall change in T term is not zero, because we have the time and we know there's a force that the hole pushes on the ball. On the right side of the equal sign, the final velocity is zero, because the ball will come to a stop inside the hole, so that term falls away. Now we can substitute and solve for F wall. If you do everything correctly, your answer will become 26,650 newtons. And we are done with that problem. If you have further questions, please address them in the comment section. The second problem says a 2 kg block is at rest on a smooth frictionless surface. The length of the block is x. A bullet of mass 0,015 kg traveling east at 400 meters per second strikes the block and passes straight through it with a constant acceleration. Thereafter, the block moves to the right at a speed of 0,7 meters per second. Ignore any mass loss of the bullet and the block. If it takes 0,002 seconds to travel through the block, use energy principles to calculate the length x of the block. That is for 12 marks. Make sure you write all your given data and then try to attempt this problem on your own before watching the solution. We will establish the directions using the compass, and you will choose east as the positive direction, which means anything that is going to the west will be negative. Let's see an animation of what happens here. The gun is shot, the bullet will go through the block, and after it passes through the block, then the block will start to move. This block has a length of x in the horizontal direction. Our goal is to find the final velocity of the bullet just after emerging on the other side of the block. We know that the principle involved there is the conservation of momentum, so we write the conservation of momentum equation, which says the sum of the momenta initial is equal to the sum of the momenta final. If you don't know how to modify the conservation of momentum equation given the collision case, please watch my video on the conservation of momentum collision cases. In this case, the equation looks like this, because the bullet and the block are separate before the collision and after the collision. In this case, I will let the bullet be big letter B or capital B, and then I'll let the block be a small letter b. Now let's go ahead and cancel all the terms that are zero. Is the initial momentum of the bullet zero? No, because the bullet has velocity initial. Then we move on to the momentum initial of the block. Is it zero? Yes, because the block was at rest initially, so that term is zero. Going to the other side of the equal sign, does the bullet have momentum after the collision? Yes, because it continues to move at a certain velocity, which we are trying to calculate. Does the block have final momentum? Yes, of course, because the block continues to move eastward at 0,7 meters per second. Then now we can substitute and leave the cancelled terms as 0. The mass of the bullet is 0,015 kg. The velocity initial of the bullet is 400 meters per second, positive, because it was going eastwards and east is chosen as positive, plus 0 for the initial momentum of the block, equal to 0,015 for the mass of the bullet multiplied by the velocity of the bullet final, plus the mass of the block is 2 kg multiplied by a positive 0,7, because the block will go eastwards after the collision. final velocity is our only unknown in the equation, so we can find the value of that, which turns out to be 306.67 meters per second. And don't forget, velocity is a vector, so we have to say the direction, which is now towards the east because we returned a positive answer. Now we want to use the impulse momentum theorem to find the force that the block will exert on the bullet. So we can change our sketch to this. We know the initial velocity of the bullet is 400 meters per second just before it strikes the block. And it is going to emerge from the other side with a velocity of 306.67 meters per second. Note that the bullet will travel a distance of x inside the block while moving at a constant acceleration. So you can basically use the equations of motion because they apply to constant acceleration, but in this case, they specifically told us to use the energy principles. So we'll go the momentum route. We know the impulse momentum theorem says F net, change in t, equals to the change in momentum. Then we can look at the free body diagram of the bullet as it goes through the block. We see that there is a force that the block is exerting on the bullet. Remember, the block is small b and the bullet is big B. This is the only force that is acting on the bullet during its motion inside the block. So that is our F net, which is a negative value because it's going in the negative direction. Now we expand the momentum equation, which says the mass multiplied by the final velocity minus the initial velocity. Let's substitute our values. F net is what we're looking for. It takes the bullet 0.002 seconds to go through the block. So that is our change in time or the contact time. We know the mass of the bullet is 0.015 kg. The final velocity of the bullet when it comes out of the block is 306.67, and the initial velocity of the bullet just before striking the block is 400 meters per second. Our only unknown is F net, which we can simply find the value of by dividing both sides by negative 0.002. Then we have a value of 700 newtons. What is the direction of this force? As we already established, it's going to the west direction. The answer I got is positive because I already placed the negative inside the formula. Now that we have the net force acting on the bullet, we can then find the distance traveled through the block. For this, we use the work energy theorem, which says work net is equal to the change in kinetic energy. The work net term becomes F net multiplied by the change in x, which is the distance traveled, multiplied by the cosine of 180 degrees because the force is applied in the negative direction to where the bullet is going. And this is equal to half of the mass multiplied by the final velocity squared minus the initial velocity squared. Remember, we wrote this equation for the bullet just so that we can find the distance the bullet travels when the velocity changes from 400 to 306.67 meters per second. And that distance will give us the length of the block. F net is substituted by 700 and change in x is substituted by x. Cosine 180 degrees is -1. That is why we have a negative in front. This is equal to half of the mass of the bullet is 0.015 kg. The final velocity is 306.67. Don't forget the squared minus 400. The squared should come before the bracket because we are squaring the 400. So it's 400 squared close bracket. Sorry for that mistake. So we notice that our only unknown here is x, which we can find the value of, and it becomes 0.71 meters. So this means the bullet travels 0.71 meters through the block, and this means the block has a length of 0.71 meters. The final example says a monkey of mass 25 kg, swings from rest on a rope of length 12 meters, which is initially horizontal as shown in the diagram below. At the bottom of his swing motion, he picks up a bunch of bananas of mass 5 kg and swings with them until coming to a stop. Calculate the maximum height above the ground reached by the monkey with the bananas. This one is 12 marks. Remember to write all your given data and then try this example on your own and then come and verify if you did everything correctly. We will take the position of the bananas as our ground position. This means the height here is 0 meters. Since the length of the rope is 12 meters, this means when the monkey is straight on the ground, he will have traveled through a length of 12 meters. And so we can say the length from the position of the monkey to the ground is 12 meters. And we'll call that position A for reference purposes. Then there goes the monkey. At this position, the monkey is vertical. And it is just before he picks up the bananas. So I'll call that point B0. Let's let the monkey be 1 and bananas be 2. This will help us write our equations neatly. I'll call the position of the monkey from position A to position B as part 1 of the problem. What we know is that the mechanical energy is conserved when the monkey swings from position A to position B0 just before picking up the bananas. So we write the conservation of mechanical energy for the monkey. Let's go term by term and cancel terms that are zeros. At point A, does the monkey have kinetic energy? No, because it is initially at rest, so no velocity initial. Second term, does the monkey have potential energy at point A? Yes, because it is at a height of 12 meters above the ground. On the other side of the equal sign, we know the monkey will have a final velocity at B0, so that term is also not 0, but the monkey doesn't have a height at that position, so we can cancel the potential energy term at B0, which is the final potential energy. Then let's substitute our values, leaving the cancelled terms as zeros. The mass of the monkey is 25 kg, multiplied by 9,8 for G, multiplied by the initial height of 12 meters. This is equal to 1 over 2 into 25 for the mass of the monkey, multiplied by the final velocity of the monkey at point B0. So the only unknown here is V1 final, which becomes 15,34 meters per second. Then I want you to look carefully at the monkey and the bananas, because this is a very important concept that happens. So look directly at the monkey and the bananas. So you can see there's a split second from B0 to B1 where the monkey picks up the bananas. So you can see the monkey doesn't change position, but it does pick up the bananas. And something interesting is happening here. This moment, we have an inelastic collision because the monkey will pick up bananas that he'll then move away with. So he's going to lose some of his initial velocity. Then energy is not conserved because the collision is inelastic. So we go to momentum for this part between B0 and B1. Then part 2 from B0 to B1. The conservation of momentum says the sum of the momenta initial for the monkey and the bananas is equal to the sum of the momenta final for the monkey and the bananas. If you are not sure with momentum, please go watch my momentum video. The expanded equation will look like this. Momentum initial of the monkey plus momentum initial of the bananas, because they were initially separate. Then on the other side of the equal sign, we have the mass of the monkey added with the mass of the bananas. This is multiplied by the same final velocity because now they move as a unit. Now we can go ahead and cancel terms that are zeros. Does the monkey have initial velocity or initial momentum? Yes, it does. Does the bananas have initial momentum before the collision? No, so that terms become zero. Does the monkey and the bananas have final velocity? Yes, just after the monkey picks up the bananas, they will have a final velocity which will cause them to swing on the rope again. Let's substitute. The mass of the monkey is 25 for M1. The velocity of the monkey initial, just before picking up the bananas, is 15,34 meters per second. Then this is equal to the mass of the monkey is 25 plus M2, which is the mass of the bananas, which is 5. This is multiplied by the same final velocity because they move as a unit. Then we can see that we have the same final velocity. The value then becomes 12,78 meters per second. So just immediately after the monkey picks up the bananas, he's going to lose some speed. Then we see the final velocity is now decreased, which means we are correct. Let's look at the final motion of the monkey with the bananas. This brings us to point C, which is at a height of h above the ground. So for part 3 from B1 to C, we see that again mechanical energy is conserved. So we write the conservation of mechanical energy equation, which then says the initial kinetic energy of the monkey with the bananas plus the initial potential energy of the monkey with the bananas is equal to their final mechanical energy. So now we consider the monkey with his bananas. I think that will make him happy. Okay, let's cancel the terms that are zeros. Does the happy monkey have an initial kinetic energy? Yes, it does, because it's going to leave the ground at a certain velocity, so that term is not zero. Does the monkey with his bananas have initial potential energy? No, because at B1 they are still on the ground, so that term becomes zero. Now, does the monkey with the bananas have final kinetic energy? Because they will come to a stop at the end of their swinging motion at position C. That term is zero. But we know they do have a height above the ground, so they will have final potential energy. Now we can substitute, leaving the cancelled terms as zeros. So we have half of, now the mass, remember, is the mass of the monkey and the bananas. So it's 25 plus 5, which is 30 kg. Multiply this by the 12,78 meters per second for the initial velocity of the monkey with the bananas squared. This is equal to, the mass is still 30 times 9,8 multiplied by the final height, which is h. Then we get a value of 8,33 meters for the final height at point C. And this, together with the part 1 of the energy principles, you are now ready to tackle any problem involving work and energy. We will do power at a later stage. Okay guys, remember to like, share, comment and subscribe. I really go out of my way to create these videos for you guys, so please return the favor. And don't forget, you can join my one-on-one live tutoring sessions. Check the description for more details. Cheers guys.